Okay, please, Frederick, you can start.
So, my name is Elena Ohai.
I will
Ah,
introduce
okay.
Eleonora. Excuse me. Yeah, so sorry. Yeah. Thank you, Eleonora. So it is a pleasure today to welcome Olena, okay, from the Department of Mechanical Engineering at the University of Aveiro in Portugal. Olena obtained her PhD in Material Science and Engineering in November 2009. Her main scientific interests during PhD degree were processing and characterization of ferroelectric films and ceramics, and her postdoc activity focused on the materials for energy harvesting and storage, such as thermoelectrics, piezoelectrics, as well as materials for solar cells. And her current work is on 1D and 2D carbon family materials and different composites. And today, Olena will be talking about porous aerogels of reduced graphene oxide for energy storage. So please, Olena.
Yeah, thank you very much for introduction. Yes, today I will tell you something about reduced graphene oxide that I use for materials for harvesting and energy storage. And because I use short-time scientific visit supported with this, by this course, I include some part of material, some part of results for this presentation. So this is Portugal, you know Portugal, and Aveiro is close to Porto. This is our university. We have campus, beautiful weather, beautiful nature. You can visit and see. We have 16 departments, different polytechnic schools, high number of students. You can come and see it. And as I already said, I had a short-term scientific mission in Krakow, in Poland. It was a group of Professor Sulka in Faculty of Chemistry. We did some measurements. This is a department outside and inside. It was very beautiful for me, short time, but I remember this is for all my life. So this is Krakow. And let's start with my presentation. We have many problem appears every day with our comfortable life. We need to think about safety, about quality, and probably one of the biggest problem is energy. We need it as much as possible every day because we have more and more devices, cars, etc. And now we have know that we can produce energy from obtain energy from different source, for example wind energy, but it cannot be during all times because of many problem of weathers, transportation, etc. Solar energy again is effective method, but effective efficiency not high yet. Wave energy, thermoelectric, piezoelectric, but in all of this case, we need to save energy, energy storage. And based on the basic knowledge, you know that we can save energy in capacitors. I will try to make a point here. It's like two metallic electrodes and one ceramic or filled dielectric inside, and we have energy here. Or we have typically lithium-ion battery when we have cathode and anode, and ion of electrolyte moves from one to another side, and we have charge. And between those two devices, we have supercapacitors. Supercapacitors can be divided for two different types, double layer capacitor and pseudo capacitors. Difference is here is we have charge, and energy storage in electrolyte, in interface between electrolyte and surface of electrode. But here is also in electrolyte interface and on top of surface of electrode. So the main difference between supercapacitors and lithium battery, not only lithium battery, but in battery in general, we can observe in charge-discharge curve. So in case of supercapacitors, it will be fast charge and discharge, triangular, as you can see. And in case of battery, it's slowly charge and discharge, and this is visible plateau when we have in this case interaction inside in material and back. So you know that battery can be used in different devices, for example in your mobile phone, but supercapacitor is also included in your telephone, in your mobile phone, but not a lot of people knows about that. So if you will see a popular Ragon plot, capacitors has high specific power but low specific energy. Battery has high specific energy but low power. Supercapacitors are between them and they can show very high power but not so high energy. So what formula? What we use for calculation energy density for supercapacitors, it's low, but for battery, it's high. As you can see, it depends on capacitance of cell. And in case of power, it's calculated by this formula. Okay, for supercapacitors, we can obtain high value, but for battery, we know that it's low. So as you can see, the optimal variant can be if you will combine high power density and high energy density. But at the moment, we don't have this ideal device. So people call it like a hybrid device. So low capacitance electrode, EDLS observe the capacitors, and high capacitance battery type electrode. And we expect very high total capacitance. But if you will see literature, capacitive electrodes is here, you see, in comparison with battery type, which more higher. Here is capacitive and battery type, capacitive electrodes and battery type. But when it will combine in hybrid device, in total, it's still to be low. For example, 50, but 8, 150 and 1020. So it means that in reality, total capacitance of our hybrid device will be limited by low capacitive electrodes. So we need to think how to increase this capacity of electrodes and what materials can be used. And the objective of my study for this presentation was to study reduced graphene oxide as based electrodes for sodium ion studied in sodium ion electrolyte, because you know again that lithium is not so high amount in comparison with sodium, and we need to think about our nature, about cost for our device. So we study RGO for sodium supercapacitors. Of course, in the beginning it was graphene. Graphene is one layer of carbon, and in ideal case, you will have specific surface area, very high electron mobility, optical transparency, etc. And it can be used in many application area. However, if you want to obtain monolayer, you need to use chemical vapor deposition or MBA method. So it's expensive, and in results you will have very small size. So it's not easy. And many people use reduced graphene oxide. What means reduced graphene oxide? You can prepare graphene oxide solution, for example, by Hammers-based method. So you use graphite. After that, add some acids. You obtain graphite oxide, and you can do functionalization or without it, as you. But in case you prepare graphene oxide solution, unit reduce it. And typically we use thermal treatment at higher temperature, or you can use chemical treatment, for example, hydrogen hydride, and obtain reducing graphene oxide. So we start from the simple vacuum filtration method to obtain freestanding electrodes without ports, just to have our materials, as you can see here. I will tell you later more. And we also compare it with also freestanding electrodes, but prepared from the slurry with foam here obtained by hydrothermal method. And in the last moment, we decide to use flexible textile as support, as substrate for slurry that used aerogel, reduced graphene oxide aerogel. So, first method, we use typical glasses for preparation of, let's say, freestanding membrane. Here is our filter. It is white. And we have several sizes of filter. Here is small, but it can be up to 5 or more centimeters in diameter. Here is scanning electron microscope. You can see this is multi-layer structure. We study SEM on top surface. It looks very porous, so let's say soft. This is 10 micrometers, this is 50 micrometers. Depending on the concentration of graphene oxide solution and amount of solution, we can obtain different multi-layers. It can be in my case, I know that I can obtain 5 multi-layers, but it can be up to, as you can see, I don't know, 50 or something like that. So we study Raman by Raman, calculate the ratio between two smooth, and you see it's not high. It means we have, of course, we have defects, but we have visible observations that we have reducing graphene oxide, and we study IV, study electrical conductivity, and you see we have very low resistivity of these materials. It means we have really reduced graphene oxide because, as I already said, graphene oxide is dielectric and cannot be electrically conductive. However, when we study electrochemistry, cyclic voltammogram, for example, we see that our material didn't show rectangular shape, what we are expected for this capacitive materials, and the same for charge-discharge curves. So it's very fast charge and discharge. So it means slow integration CV area, low capacitance, and we decide not to use it for next study. And our next set of samples was about preparation of reduced graphene oxide like foam and also freestanding electrodes. So we prepare graphene oxide solution and use hydrothermal processing at 180 degrees. This is our autoclave. We put solution inside, and after processing, you see here inside we have our foam here. It's dried, and we study by XRD. Yes, we have strong X peaks at about 24 or something like that, and not about 10 like for graphene oxide. So we have reduced graphene oxide. We study by ICM. You see, this is 500 micrometers and 10 micrometers. In comparison with previous, it looks thinner and much better. So we have this form, and typically for commercial electrode that used for example, for battery, it consists 80% of active material. In our case, this is RGO form, 10% of conductive additives, we use carbon black, and 10% of polymer binder, we use PVDF. We mix it, press it by hand, and make it freestanding here. After that, we cut what we need, 1 centimeter per 1 centimeter. if I remember correct, and study it with electrochemistry. And surprisingly, we have very nice, almost rectangular, at very low scan rate. It looks perfect and stable. As you can see, this is 5 cycles. However, when we start increase our scan rate, uh, in typical way, it should be increased, but area was not increased and just rotate. That means that materials is not good for this electrochemical study, and charge discharge, as you can see, also it's very fast discharge. So we also and conclude that this method is not the best. So, and we start to think about aerosols. We prepare graphene oxide solution and use graphene freeze drying process to obtain graphene oxide aerosol here. So, freeze drying, it means we freeze until 50, here is minus 60 degree. We put it in our freeze dryer. So freeze dryer, it means bottom part here and top part. This is top part for lyophilization. So when we put inside, you can see ice here. After that, we remove it on the top here. And until water disappears, it can be 24 hours or more or less. And we have copper cup because we use plastic cup. But if you will see here, it can be also another shape, rectangular, or what do you want. So, and to obtain reduced graphene oxide, we make reduction heat treatment and 180 in vacuum oven and 700 in argon by rapid thermal annealing. Here is 180 and here 700. It is visible that reduced graphene oxide obtained at a higher temperature looks more dense, let's say. And we continue study by X-ray. You see position of peak in case reduced graphene oxide annealed at 180 is at lower position in comparison with reduced graphene oxide at 700. What it means? It means that interlayer distance decrease with increasing of temperature. It means not so not big space for ion of electrolyte, we leave it. So in case of Raman, we also make Raman study. And as you can see, intensity ratio between intensity D and G peaks increase with temperature. It means that the defects increasing. XPS for this reduced graphene oxide aerosol show us that, of course, the main difference with the oxygen, that oxygen groups almost disappear with increasing of temperature. You see intensity for this for 180 and for 700. So it means for that reduced graphene oxide aerosol annealed at 180 still has some oxygen functionality groups after annealing in comparison that we didn't observe almost in aerosol at 780. Again, we mix with conductive additives. Here we use carbon nanotubes. We think that we already have publications that carbon nanotubes can increase electrical conductivity in case we will mix it with reduced graphene oxide. So we try to increase electrical conductivity and use it as conductive additives. And also we use PVDF, similar with previous one, to obtain slurry and cover it on and into textile substrate. We check flexibility was nice if you want to use it for flexible electronics, for example. And check electrochemical properties of single electrodes. We use sodium electrolyte, and this is CV and charge discharge for electrodes with aerogel obtained at 180. And this is with aerosol at higher temperature. As you can see, difference in ratio. This is 6, this is 3, 2 times. And also we have some pseudo capacitance here. It's visible in comparison with this one. And when this is impedance, both of them show capacitive behavior. Uh, Even reduced graphene oxide obtained at 700 show a bit higher capacitive properties. When we calculate data, capacitance for first type of electrodes with RGO at 180 show us in 3 times higher value. And this one we use for preparation of full device, symmetrical capacitors. We use two equal reduced graphene oxide CNT PVDF electrodes with this electrolyte and special membrane. And as you can see, we study cycling. It was 10,000 cycles. We have almost rectangular shape and triangular, almost ideal. For long cycling, in total, it was more than 140 hours. And of course, our idea was to study XPS after. So this is for fresh electrodes, carbon and oxygen, and this is after cycling. So almost nothing happens in case of carbon, and I cannot say that something special happens with oxygen. So it's very chemically stable materials and good electrochemical results can obtain for that. So this is just visible difference between hydrothermal process and freeze drying and annealing. So the same amount of solution was used for hydrothermal and for freeze drying and annealing, and you can see the difference between volume. It's visible. The hydrothermal gives us dense structure, not like freeze drying. So short summary is like that aerogel for supercapacitor electrodes is much better than vacuum filtration and hydrothermal electrodes, hydrothermally obtained electrodes. RGO, aerosol and composite electrodes give us advantage to obtain lightweight active material and electrodes. Great electrochemical stability, mechanical stability. We can use sodium electrolytes, not obliged to use lithium electrolyte. But of course, capacitance strongly depend on annealing temperature and should be increased because this is our goal. So thank you very much for your attention, and I am open for presentation, for questions.
Thank you very much, Olena. Thanks for this great presentation and a very interesting recent result you have presented. We have time for a few questions. So you can either start speaking, raise your hand, it's up to you in the audience. Okay, so I may start with one quick question. So it seems that you have identified the optimal conditions, I guess was in the vacuum condition from the aerogel. What is the next step that you plan for improving the system?
As I say, use that we didn't use functionalization. We use simple material, but I think we already have some addition of ammonium, and it was perfect. Microstructure changed a lot, and I believe that we will obtain a higher value of capacitance. And of course, we will study it in battery with battery electrodes in hybrid supercapacitors, not in symmetric supercapacitors. But to be honest with you, my contract finished, and I don't know who will continue this.
Oh, okay. And just another quick question: you think the increasing the temperature is because you have tried two temperatures in different conditions, but increasing the temperature would help, or it's not
No,
necessary?
no. As you can see, when we increase temperature, we increase electrical conductivity, but oxygen groups disappears. And I believe that there's oxygen functionalized groups that we still keep at lower temperature will help to increase capacitance.
All
So we
right.
need to find balance between increasing electrical conductivity, but have oxygen inside on top of electron.
Maintaining, yeah,
Yeah.
oxidation. Fine. Okay. Other question from the participant? No? All right. So if we don't have question, then we can thank Olena again. Thank you very much. It was a
Thank you.
great pleasure to have you speaking today. Um, one short message here. If you one of you like to present her or his activity at the webinar, please don't hesitate to contact me, Frederick Kunen. I'd be happy to, 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 to talk to you and schedule a presentation of your work. Someone raised hand, I guess. I missed it.
I think Elizabeth.
Oh, Elizabeth. I don't see Elizabeth. Uh, uh, uh. Elizabeth, if you want to talk, please, you can start speaking with your microphone on. Oh, okay. Thank you. No problem.
Okay.
Yes, so please, it's fine. It's no worries. So please, don't hesitate to contact either Eleonora or myself if you wish to present your work at the next webinar. It's once a month, and we have open slots in 2025. So please don't hesitate to contact us. Uh, then, if there's no question, then I wish you all a very good day. And thank you again, Olena, for this presentation. And have a great day.
Thank you, and sorry for this technical problem.
No, don't worry. It happens. That's why we connect early, because then we have time to fix it. It's no problem. Don't worry.
Thank you.
Thank you very much. Bye bye.
Ciao.